Hi, welcome to my pre-end semester presentation for Project 2, the foot pressure mapping system. In this video, I want to talk briefly about the logic behind the algorithm we used for the system, and then go over the C++ and MATLAB code, and then talk in detail about what I hope to achieve in the next 2 weeks, or at least how this method could hypothetically be taken forward. So just to state at the outset, there are a large number of foot pressure mapping systems available commercially that generate a considerably more accurate pressure map than the one we're hoping to design. Our main goal is cost effectiveness, and with that in mind, we've attempted to minimize the number of sensors that we've needed to generate an accurate pressure map. Now, a large number of methods were considered while we were attempting to do this, including spreading the sensors randomly about the sole of the foot and using Lloyd's algorithm or another 3D curve fitting algorithm. But none of those made important use of a specific assumption, and it is for that reason that I decided to develop my own algorithm. It is not a very complicated one, but it makes use of the assumption that when a convex surface comes in contact with a flat surface, the pressure function it generates always has a form like that. And that's not to say that the peak is in the center, or certainly not to say anything about the slope of the function, but simply that it has only one peak. And if you notice that if you look at a foot from behind, the heel and the arch are both convex surfaces. They have one maximum point where they come in contact most with the ground, and it peters off to both sides. So using the Nyquist theorem, considering that we have the values of the outlines and then two sensors along the line, you can get a pretty accurate estimate of the pressure as it varies along that particular row. And of course, at the metatarsal heads, you start to see the foot shape become a little more concave. It comes down a little bit more at the big toe and at the little toe than it does in the center. So there you will likely see a pressure function with two peaks, which is why there are three sensors there, as well as the outline points. But with all of this data, you can generate a reasonably accurate estimate of pressure along each of these lines. And now that you've done that, and you've got 1, 2, 3, 4, 5, 6 lines along the y-axis, you can start generating the pressure for each of the points along the y-axis rows. And using this method, you can then generate a full pressure map because you've got the values along each of the x-axis rows, and then now you've got it along each of the y-axis rows. And we've used 49 rows by 21 columns for this system, which generates a reasonably accurate graph of the pressure. Now I'm just going to talk about the input to the C++ program. This is the text file that I just wrote right now because the system isn't ready, but I just wrote it to demonstrate the code. So the first number is the number of frames, which is just 3 here because I couldn't be bothered to write more. And then the next number is the number of sensors, which is 14. And then the next 14 lines are the positions, the x and y positions of the sensors. So that's where the sensors are located on this 49 by 21 grid. Um, the next 49 rows are the outline values of the foot. So what we've done there to make it simple is for the 0th row, since the foot doesn't intersect the 0th row, you've written 0 and 0, and the same for the first. And then for the second row, the foot intersects it at 8 and 12, the x-intercepts of the outline, and that's all it is. The intercepts are we continue to write the intercepts all the way down to the 48th row where it's 0, 0 again. Um, After you get the outline of the foot, the next columns, which is the number of frames times the number of sensors. So since there are 3 frames and 14 sensors, there are 42 points at this point. Um, so you have the first number is the frame number, the next number is the sensor number, and then the value of that sensor at that frame. So for the first 14 inputs for the 0th frame, and you get the value of each of the 14 sensors during the first frame, and then the next 14 are for the second frame, and the next 14 are for the third frame, and so on. And then the C++ program generates an output file of this format, which of course just looks like a garble of numbers right now. but it's actually the pressure values at for each frame for each row and column. So you see a 49 by 21 grid for the first frame, which looks like that, and then a similar matrix for the next frame and the next frame. And of course, it's really difficult to make out exactly what you're seeing here. So I'm going to demonstrate this on MATLAB using a couple of very simple commands. Just make x from 0 to 20, y from 0 to 48, mesh x and y, and then use a simple mesh plot of x and y and the FP map out, or a surface plot which generates something like that. Now, what you're seeing here is a high pressure at the heel, because that's how I've written the inputs, and a low pressure near the toes and metatarsals. So you can see the red area indicates high pressure, and you can see the outline of the foot is pretty accurate here. And of course, when I'm running the actual program, I will make each frame one frame and generate a video of how the foot pressure varies from frame to frame. But for now, I've just done it for one frame. Um, so that concludes the state of the software, the presentation of the state of the software right now. I'm just going to talk briefly about how this could be improved, and specifically about how this system could be made real time. I'm running Linux and ROS Groovy in a virtual machine, which works really well. And I'm just going to quickly go over how this could be made real time using a simple Arduino microcontroller to get the inputs. So this is a really simple Arduino program that just gets the input from a pot pin and displays it on a serial monitor. The pot pin is connected to analog in 2, and I'm just gonna wire this like to like. So I've got 5 volts ground and signal wired to 5 volts ground and 2, which is the analog pin. The signal is from the pot pin, and this method is taken from a YouTube poster called Darkman Fanboy, and it uses a ROS bridge protocol developed at Brown. So it's pretty much exactly what he did in his video to wire a range sensor with HTML5 and JavaScript, and the video is available on YouTube. So I'm gonna change my directory to where I want to run ROSBridge, and then start a ROS core. All of these details you'll have to look up online if you want exactly how each of these ROS functions works. I'm going to set up a ROS core in the background, and then run a ROS bridge in the background again. And then with a SOCAT command, you can get the input of the pot pin displayed on the screen. So as you can see now, the input is around 700. And if I turn the pot pin, it goes right down to about 46, 45. And then I can turn the pot pin back up, and it goes back to nearly 700 again. So of course, using these values, you can then pipe the input from the Arduino through Netcat, and then write a HTML5 and JavaScript document to display the pressure map on the screen in real time as the input is coming in from the Arduino. I haven't written the HTML5 or JavaScript code yet, but it shouldn't be too difficult to do as long as the algorithm runs fast enough to generate the map as the input is coming in, and that's something I'll have to test when the pressure mapping system is ready. But that concludes my presentation for Project 2. Thanks for watching. I hope you've enjoyed it.